Okay, let's unpack this. So if you're relying on large language models in production, right, maybe for generating code or powering a RAG system, retrieval augmented generation.
Or even handling complex reasoning tasks. Lots of applications now.
You are basically relying on an architectural stack.
Yeah.
And the thing is, it harbors this fundamental weakness. We're talking deep, potentially costly instability.
Absolutely. It's a hidden brittleness.
So our mission in this deep dive is to expose that. We want to look at why LLMs sometimes just flip their answers or fail basic robustness tests, even under edits that seem, well, totally harmless.
Yeah, things that shouldn't break them.
And we're also introducing the next generation of diagnostic tools. There's this suite called Wilson, and it's designed to actually anticipate these failures.
Right. By looking deep inside the models, let's say, its mathematical core, its internal workings.
Okay, so not just looking at the final output, but the process.
Exactly. The problem you first mentioned, it's not just theoretical, right? It's a massive time-consuming drain for engineering teams.
Give us an example.
Sure. So imagine a developer fine-tunes a model. It looks perfect in QA. Everything's great.
Okay.
Then, in production, they authorize what seems like a minor speed optimization. Maybe reordering passages fetched by the RAG system to get better parallelism.
Makes sense. Standard optimization technique.
But suddenly, the output flips. It goes from a correct summary to maybe a confident hallucination.
Wow. Okay, so we're talking about situations where the meaning of the input hasn't changed at all,
Semantically identical.
but the model's output completely changes.
Exactly. Or something of maybe even more subtle, like in code generation.
Okay.
Our sources show you can take a perfectly working function and just rename a local variable. Let's say you change stack pointer to just sp.
Which functionally means nothing, right? The code does the exact same thing.
It should. A robust code LLM should treat that as identical. It's called alpha renaming in compiler theory.
But they don't always.
Often they don't. That simple renaming can cause the model to fail a basic benchmark test it previously passed.
Okay, that right there violates the basic principle of stability or invariance. The model should be invariant to changes that preserve the meaning.
Correct. But it isn't.
And those failures, they lead to wasted dev cycles, rollbacks, basically slowing down the whole deployment pipeline.
Precisely. It's a huge hidden cost, and that's why we need a new approach. Traditional fixes, like constantly retraining the entire model.
That's just unsustainable. Too expensive, too slow.
Exactly. So Wilson offers something different. It's a minimal, post-hoc diagnostic suite. Think of it like a powerful X-ray for the transformer.
Post hoc meaning after the model's trained.
Yes. You run it on the existing model. It detects these potential instabilities by analyzing the model's internal geometry.
Internal geometry. Sounds complex. What does that mean, practically?
It's about the specific mathematical paths information takes through the model's hidden layers. Wilson analyzes these paths without needing any retraining or changing the model architecture itself.
Okay, so this isn't about trying to train a fundamentally safer model from scratch. It's about getting, perfect visibility into the vulnerabilities of the model you already have deployed.
That's the key insight. That's the difference. We frame Wilson as this crucial tool for both reliability and throughput.
How so?
Well, it gives development teams the confidence to maybe approve some higher risk optimizations, things like kernel fusion or operator parallelism stuff that speeds things up.
Because they can now see where the potential failure points are before they deploy the change.
Exactly. They can anticipate the problems rather than react to them after they cause damage.
Okay, let's dive deeper into those failure modes. The sources you mentioned seem to point to two main technical reasons why this stability breaks down. The first one you touch on, the invariance break.
Right. This is when the model treats two inputs that mean the same thing as if they're totally different.
Like the code example, renaming psi to z. Why should the model even care?
Well, it cares because during its massive pre-training phase, the model learns statistical biases. It's not really understanding code like a compiler.
Oh, okay.
Identifiers like stock or maybe temp or I, they appear billions of times. They develop specific statistical weights, or what we call local logits. They have associations.
So the model isn't processing the code based purely on its logical structure. It's using a kind of sophisticated pattern matching based on what it saw in the training data.
That's a great way to put it. It's learned statistical correlations. So changing the identifier, even though it's logically irrelevant to the function, shifts those subtle local statistics Just enough.
Enough to change the internal state.
Enough to nudge the hidden state vector. And if the model was already making a decision near a very thin boundary, say, deciding between outputting return true or return false.
That tiny nudge pushes it over the edge.
Exactly. That tiny internal shift flips the final token prediction. The invariance, the expectation that the output shouldn't change, is broken.
Okay, that's the statistical fragility. What about the second source? You mentioned order sensitivity. This sounds more like a hardware or numerical issue.
It is. This is where we bump right into the limits of how computers actually do math, specifically with finite precision numbers.
Right, because these huge models, they almost all run using low-precision formats, like FP16 or BF16.
Almost universally, yes. To save memory, to speed up the calculations, it's essential for making them feasible.
But when you use those formats, the normal rules of arithmetic, they don't quite hold up perfectly, do they? Because of rounding errors.
Precisely. Even if the errors are tiny in the space of real numbers, theoretically.
Can you give an analogy?
Sure. Think about calculating, say, a complex sum. If you add up all the positive numbers first, then subtract the negative ones, you might get a slightly different result than if you added and subtracted in a different order.
Even though, mathematically, with infinite precision, the result should be identical.
Right. Because the computer rounds off tiny fractions at different stages depending on the calculation sequence.
And the sources say this exact thing happens inside the transformer, especially during optimizations like kernel fusion.
Yes. When you fuse or reorder operations, maybe two attention steps or matrix multiplies, let's call them path A and path B. In pure math, they're equal.
But in low-precision floating point,
they can differ by a tiny amount due to different rounding sequences, maybe just $10, $3, a really small delta.
That's enough.
It can be catastrophic. If the model's internal state, specifically the attention logits, are very close together, the sources call it a razor-thin tie boundary. That tiny perturbation from the rounding difference
is enough to change which token gets picked as the highest probability one.
Yes. It flips the top token. It's basically a chaotic system effect. A minuscule change in the internal calculation leads to a completely different output.
Wow. Okay, so we have these two powerful forces messing things up. Statistical biases breaking invariance and hardware limits causing order sensitivity. Given these seem pretty fundamental, why can't we just, engineer the transformer architecture itself to be more robust?
That's the logical question, but the existing fixes have major drawbacks.
Like what?
Well, you could try architectural fixes, maybe enforce certain symmetries, but that really restricts the kinds of models you can build, maybe limits their power.
Okay.
Or you could go the formal verification route, mathematically prove stability.
Sounds great, but I'm guessing it's slow.
Incredibly computationally heavy, way too slow to run routinely during inference in a production setting. It would just kill your throughput.
So we need something else, something fast, cheap, that works with the standard transformer we already use.
Exactly. A diagnostic that travels with the existing architecture, not requiring a whole new one.
Okay, this is where Wilson comes in. Since the traditional methods are too slow or restrictive, the Wilson approach looks at the problem geometrically. You said geometry earlier.
That's the core idea. It treats the transformer network like, a sort of grid. Imagine a grid where one axis is the token position in the sequence, horizontal, and the other axis is the layer depth, vertical.
Okay, position and layer.
And as information moves through this grid, the operations, the attention mechanism moving information across positions, and the layer transformations moving it vertically act like transports.
Like moving a little packet of information around the grid?
Exactly. Now, in a perfectly smooth, ideal mathematical world, the order wouldn't matter. Moving up one layer, then across one position, should give you the same result as moving across first, then up.
They should commute, mathematically speaking.
They should commute. But because of all the non-linearities in the network, things like activation functions, layer norm, which isn't easily reversible, and that floating point noise we just talked about.
The order does matter. The path you take changes the result.
Precisely. The path warps, the grid isn't flat. That simple commutation rule breaks down. And that warping, that non-commutativity, is exactly what Wilson is designed to measure.
How? What are the tools?
It uses two main geometric signals. The first one is called inverse-free curvature, written as cap and fair.
Curvature. Okay, like in physics. Measuring how space is warped. Here we're measuring how the information path inside the network is warped.
That's a perfect analogy. High curvature in physics means space-time is strongly bent. High kappa here means the information path is highly sensitive to the order of operations in that local region of the network.
So it measures the holonomy, how far off you end up if you travel around a tiny closed loop on that position layer grid.
Exactly that. If you go up, across, down, and back, do you end up exactly where you started? High curvature means no, you're offset, the path matters.
Now, why the inverse free part? That sounds like a technical detail, but maybe an important one.
It's absolutely critical because many core components in a transformer, like softmax or layer norm, are essentially one-way functions. They're not globally invertible in a mathematically clean way.
Meaning you can't just run them backwards easily to undo their effect.
Right, and standard geometric tools often rely on being able to compute inverses. If you can't compute an inverse, those tools break down.
So Wilson found a workaround.
A very clever one. Instead of needing an inverse, Kappa works by comparing two different computational paths specifically. Paths calculated using Jacobian vector products, or JVPs, which are efficient to compute.
Okay.
These two paths start at slightly different points but are mathematically constructed, so they should end up representing the same underlying direction. In the hidden state space, they end in the same fiber, technically speaking.
So you compare where they actually end up.
Exactly. By comparing the endpoints of these two carefully chosen forward paths, we can deduce the local curvature without ever needing to compute a problematic inverse.
That sounds really elegant. So what's the actionable insight? What does a high happy tell you?
A large kappa score acts like a flashing red light. It flags a specific region, a particular layer and token position as an order-sensitive hotspot.
Meaning that's where things are likely to break.
That's where you predict invariance, failures, or order sensitivity issues are most likely to occur. If you see high curvature, optimizing near there, or even slight perturbations, could risk flipping the output.
And low curvature means?
Low curvature suggests that region is geometrically stable. It's safer ground for doing more aggressive optimizations, like fusing operations.
Okay, that's curvature. What's the second tool? The activation commutator, delta E. This sounds maybe more direct.
It is much more direct, yeah. It specifically measures the order sensitivity between two chosen submodules in the network. Let's call them A and B.
Like two specific layers, or maybe an attention block and an MLP block.
Exactly. You pick the A and B you're interested in, maybe because you're thinking of fusing them or running them in parallel.
And how do you measure it?
You run a calibration batch of data, just some typical inputs, call it $6. Then you compute the output both ways. A then B, so we B then A, so BA.
And you measure the difference between those two results.
Precisely. You calculate the norm of the difference. BAX, that value is your commutator, delta ABX.
So if that number, delta A, is high.
It's a direct warning sign. It tells you that reordering or fusing A and B carries a significant risk of causing the final output to drift or change unexpectedly.
So it's a predictor of drift. Does it correlate well with actual problems?
Yes, the sources show a strong correlation. They measure it with all outer between a high commutator value and the actual output divergence you see if you do go ahead and perform a safe reordering or fusion. It really works as a predictive signal.
I have to ask again about the cost, though. These diagnostics for Kappa and delta AB, BI, they run post hoc, but they still add computation time to your inference pipeline, right? Is that overhead acceptable?
That's always the trade-off. The target mentioned in the sources is around 10–20% overhead at default settings.
Which still sounds like a hit to performance.
It is, but you have to weigh it against the alternatives. What's the cost of a catastrophic failure in production? Or the massive cost and delay of a full retraining cycle if something breaks subtly? And crucially, these diagnostics are designed to be relatively cheap. They use techniques like JVP probes, which are much faster than calculating, say, full Jacobian or Hessian matrices. It's engineered to be efficient enough.
So it's an upfront, manageable cost to prevent potentially huge latent costs down the line.
That's the idea. Pay a little now to avoid paying a lot later. Okay. Before we jump right into all the cool ways you can use these signals, we need to talk about something just as important. Reliability, making sure the measurements themselves are trustworthy.
Makes sense. What's the issue?
The issue is something called gauge freedom in the hidden states of the transformer.
Gauge freedom. Okay, need an analogy for that one.
All right. Imagine you're trying to map the features represented by the hidden states, but the internal coordinate system of the model isn't fixed. It can sort of rotate freely without changing the model's overall function.
So if you run the model once, maybe a certain feature corresponds to north in the hidden state vector space.
Right. but run it again, maybe with a different random initialization seed during training, or even just slight numerical differences, and that same feature might now correspond to east.
Even though the model is doing the same job.
Exactly. The internal representation isn't unique. It's only identifiable up to these rotations, technically rotations in the orthogonal group, or $D.
So if the internal map keeps spinning around, the diagnostic data you collect, like saliency scores or where the curvature is high, won't be consistent from run to run.
Precisely. You couldn't reliably use it for, say, continuous integration checks because the results would vary even if the model's actual behavior hadn't changed. It kills reproducibility.
Okay, that's a problem. How does Wilson fix the spinning map?
It includes a specific gauge-fixing pipeline. It's a two-step process applied before logging the results.
What are the steps?
First, it whitens the features. That basically normalizes them, gets rid of simple scaling and correlation issues. Second, it uses something called Procrustes alignment.
Procrustes, like the figure from Greek mythology.
Sort of. Think of it as exactly. So you use the activation commutator delta AB to check the sensitivity between processing different passages. Calculate delta between processing passage 1, then passage 2 versus passage 2, then passage 1. Passages that show a low delta A value between them. They're independent. You can safely shuffle or parallelize their processing. The order doesn't significantly impact the outcome.
But if you find a pair of passages with a high delta AB,
that's your warning. Their sequential order must be preserved. They are context-dependent in a way that risks messing up the final output if you change their order. So Wilson tells you, parallelize these, but keep those sequential.
That's really direct guidance for optimizing the R pipeline safely. Okay, what's next? Fine-tuning audits.
Fine-tuning often feels like a bit of a black box, right? You tweak the model on new data, hoping to improve performance on one task.
Without breaking its performance on everything else, or making it more brittle.
Exactly. You often regress on core capabilities or invariances without realizing it. Here, you can use the curvature map, CUPEN.
How? Compare before and after?
Precisely. You calculate the curvature map before fine-tuning and then again after. If you see a statistically significant increase in curvature in specific layers or positions after tuning,
that means you've introduced instability, made that part of the model more sensitive.
Yes. It's a direct signal that the fine-tuning has potentially made the model more brittle in that area, more prone to invariance failures. That fine-tuned checkpoint might need to be flagged or even automatically rejected by a CI gate.
So it acts as an automated check against introducing fragility during tuning. Very useful. What about complex reasoning, like chain of thought, COT stability?
We all know COT prompting can be powerful, but also weirdly sensitive. Just changing the prompt slightly, like from let's think step by step to let's reason through this logically, can sometimes give wildly different results.
Yeah, that fragility is well known.
Those different prompt templates essentially activate different internal reasoning pathways in the model. You can use the commutator delta AB to measure the sensitivity between these different reasoning pathways.
How would A and B be defined there?
A could be the model state after processing the input with COT template 1, and B could be the state after processing with COT template 2. A high delta between them suggests the reasoning process itself is fragile.
Meaning the model's final conclusion is highly dependent on the exact phrasing used to elicit the reasoning.
Exactly. It indicates that the reasoning pathway isn't robust.
And if you detect that fragility, what's the remediation?
It suggests you probably need more robust decoding strategies at the end. Don't just take the single highest probability answer. Use techniques like ensemble methods, running multiple prompts, or self-consistency decoding where you sample multiple reasoning paths and take the majority answer.
Okay, so the commutator flags the need for those more complex but more reliable decoding methods.
Right. And finally, stepping back, the curvature map serves as a guide for general optimization across the entire system. Any engineering team looking to speed up the inference engine, maybe by fusing adjacent linear layers or parallelizing parts of the attention calculation, can use the curvature map as a guide.
They look for the low curvature zones.
Exactly. They can confidently apply those aggressive speedups in regions where kappa in is low, knowing that the geometric stability there makes it unlikely to break the model's output. But they should avoid such changes in high curvature zones. It helps target optimization efforts safely. #tag outro.
Okay, so let's recap. We've established that these incredibly complex LLMs can break in surprisingly specific, almost mathematical ways.
Right, either due to statistical quirks learned from the data, like sensitivity to variable names, which breaks invariance,
Or due to the fundamental limits of computer arithmetic. The floating point rounding errors causing order sensitivity.
And we've seen that Wilson offers a new way to detect these issues before they cause problems. It provides these model-agnostic geometric signals.
The inverse free curvature, telling you where the internal paths are warped and unstable.
And the activation commutator, delta AB, directly measuring the risk of reordering specific operations.
And critically, these signals are made reliable using gauge fixing.
Right, so they can act as cheap, actionable thresholds or guardrails in deployment pipelines, guaranteeing reliability while still allowing engineers to push for safe speedups.
This whole deep dive really seems to hinge on this connection between the model's internal geometry and its external behavior.
Yeah.
We learned that the stability, whether the model flips its answer from a tiny, seemingly irrelevant change like renaming a variable or reordering archive passages, is directly tied to how its internal operations, its layer and attention transports, commute or don't commute.
It's quite fundamental.
So it raises this, I think, really profound question for anyone working with or deploying these systems. If a model's reliability is so closely linked to these almost invisible local mathematical properties, this internal geometry, this curvature, this commutativity, does that change how we should think about building robust AI? Is the path forward less about just throwing more data and parameters at the problem, and maybe more about finding mathematically elegant ways to enforce or encourage this kind of geometric stability throughout the network's core?
It certainly suggests we need to look much more closely at the stability of the transport mechanism itself.
Not just the sheer size of the model or the data set. Something to think about.